All right, next up in section 4.3, we're going to talk about what are called subspaces. Okay, so subspaces. And the idea is that we're going to start off with a vector space V. Okay, so we're going to start off with V. And we're going to say that a subset, so in other words, a collection of some of the elements of V, maybe all of them, but some of them, is a subspace. So here's the picture, just in case what I said doesn't quite make sense. Take any vector space V that you like. Take any subset W. Okay, so it's a space living inside V, and it could be V itself. We say that every set is a subset of itself, so that's totally fine. But anyway, so this is the kind of picture to think about. W is a subspace of V if W itself is a vector space under the same operations. So under the same operations as V. Okay, so that's what a subspace is it's a subset that's also a vector space under the same operations as V. So, for example, the set that we talked about last time, S, which is the set of all vectors of the form x comma 0, where x was a real number, is a subspace of R2. Okay, so it is a subspace of R2. Again, I'm thinking of R2, so just to iron this out here, I'm thinking of R2 as the set of all vectors x, y, where x and y are in R. I previously defined it as the set of all points, x comma y, but remember that we had that nice correspondence between a point and a vector. Okay, so I'll let you go back and think about that a little bit, but you can think of R2 as both a set of vectors or a set of points. It's really kind of the same thing there. Even though vectors and points aren't the same thing, thinking of R2 as a set of vectors or a set of points, you can get away with there. So S is a subspace of R2. A little bit more interesting, if we were to take, so we could consider V to be the set of 2 by 2 matrices, and maybe we can let our subspace W, I should call our subspaces W just to be consistent with the book, but we could take W to be the set of 2 by 2 matrices of the form A, B, 0, C. So maybe the set of upper triangular matrices. That's going to be a subspace of M2, 2. Okay, so again, you can check that if you add any two matrices of that form, you get another one. If you take a matrix of this form and multiply by some scalar k, you get another matrix of this form. All the other properties are satisfied. Okay, but these are subspaces. Another example that's important enough that I wanted to mention it. So let's say that our vector space here is the set of n by n matrices. One example of a subspace, and this is a good one, is W could be the set of what are called symmetric matrices. I'm not sure if I've used this word before or not, but W is the set of symmetric n by n matrices. And a matrix A is called symmetric if it's equal to its own transpose. So if A is equal to A transpose, we say that A is symmetric. And so it turns out that the set of symmetric matrices is going to be a subspace. And all you have to do is just show that the sum of two symmetric matrices is symmetric. If you take a symmetric matrix and multiply it by a scalar, you get another symmetric matrix. And maybe we'll do that in the coming examples here. You can think of 2 by 2 matrices if that's easier to start with. Okay, so these are all examples of subspaces.